Tonight we're going to look at something you think you already understand. Darkness. You've met it before. The bedroom with the lights off. The moment you close your eyes. The basement with no windows. You've always assumed that's what darkness is. It isn't. Not even close. Earth has never gone dark. Not once. Earth only gets dim. Real darkness is somewhere else, and it does something to the human mind that no room on this planet can do. Tonight, I'll take you down through every level of dark that exists, all the way to the bottom, and by the end you'll understand why nothing on Earth comes close to how dark space actually is. Now get yourself comfortable, hit subscribe, we begin. Somewhere in your home there is a room you would describe as pitch black. Lights off, door shut, curtains pulled tight against the window. You have stood in it before, maybe last night, and you would swear without hesitation that you could not see a thing. You were wrong, not slightly wrong, completely wrong. And the reason why is the beginning of a story that ends somewhere far stranger than a dark bedroom. Here is what actually happens in that room in the minutes after the light goes out. Your eyes carry two kinds of light-detecting cells. Cones handle daylight, color, detail, the sharp edges of things. Rods handle the dark, and they are far more sensitive, but they are slow to wake up. For the first 5 to 10 minutes, your cones make small adjustments and give you almost nothing. Then a handover occurs, the rods take over, and your vision keeps improving for another 20 to 30 minutes before it reaches its true floor. 20 to 30 minutes. That is longer than most people are willing to lie still in a dark room without reaching for a phone, which is exactly why most people go their entire lives without discovering what their own eyes are capable of. And when the rods finally take command, something quietly unsettling happens. The world drains of color. Rods cannot encode it. So the shapes that emerge out of your dark bedroom, the door frame, the chair, the edge of the bed, arrive in nothing but shades of grey. You are not seeing nothing. You are seeing in black and white, because light is still arriving. It never stopped. Somewhere along the bottom of your door, a thread of it slips through from the hallway. A router blinks. A charger glows. A street lamp presses against the curtain fabric and bleeds through the weave. If the moon is up, it's light. Sunlight, bounced off a rock and sent back down, is landing on your window right now. And beyond all of that, if you live anywhere near a city, the sky itself is glowing. Streetlights throw light upward, the atmosphere scatters it back down, and the whole night dome hangs above your roof like a lamp with a shade over it. Your room is not dark, your room is dim, and your eyes are extraordinarily good at making dim look like plenty. So go further. Drive until the towns run out. Find the most remote wilderness on the continent on a moonless night with no glow on any horizon. You still will not find darkness there. And this is where it becomes genuinely strange. Starlight alone is arriving from every direction at once. Dust drifting through the inner solar system catches sunlight and scatters it into a faint band along the sky. Astronomers call it zodiacal light, and on the clearest nights it can supply up to half the natural brightness overhead. Then there is the strangest source of all. High above you, in a layer roughly 90 to 100 kilometers up, 56 to 62 miles, about 8 times higher than a passenger jet cruises, oxygen atoms are quietly glowing green. Sunlight energizes them during the day. At night, they release that energy back as light. The air itself is luminous. Researchers call it airglow, and on the darkest nights in the darkest places on Earth, it is the single brightest thing in the sky. Think about what that means. The atmosphere that lets you breathe also refuses to let you experience darkness. It scatters, it glows, it fills in. Every square inch of sky over your head is faintly, permanently lit. Earth offers dimness. Earth has never once offered darkness. To find the real thing, someone had to leave. On February 7th, 1984, a NASA astronaut named Bruce McCandless II pushed himself out of the payload bay of the Space Shuttle Challenger wearing a nitrogen-powered backpack and did something no human being had ever done. He flew away from his spacecraft with nothing connecting him to it. No tether, no line, no physical link to anything human beings had ever built. He drifted out to 320 feet, 98 meters, a little longer than an American football field, and stayed out there for 1 hour and 22 minutes. The photograph his crewmates took has been reproduced for 4 decades, a white suit suspended against a blue planet, alone. But the detail that matters most never made it into the famous image. McCandless later described looking for stars out there and finding an enveloping darkness instead. He was floating in full sunlight, and when he looked away from the Earth and away from the sun, he was looking into nothing at all. That is not a poetic description. That is physics, and it is the single most important idea in this entire story. Here is the thing almost nobody realizes about light. You have never seen light. Not once. Not in your life. What you see is light arriving. A photon traveling through space, moving past you, going somewhere else. That photon is completely invisible to you. Light only becomes visible at the moment it hits something. It has to strike matter and bounce, or strike the back of your eye and be absorbed. Until then, it may as well not exist as far as your vision is concerned. You already know this, even if you have never put words to it. Point a laser at a wall in an ordinary room, and you see a bright dot on the wall. But the beam between your hand and the wall is invisible. Now let smoke drift through the room, and suddenly the beam appears, hanging in the air like a solid rod. Nothing changed about the laser. What changed is that millions of smoke particles are now intercepting photons and throwing them sideways into your eyes. The beam you thought you were seeing was never the light. It was the dust. Now take away the smoke. Take away the dust. Take away the air. In the vacuum outside a spacecraft, there is essentially nothing to intercept a photon and redirect it toward your eyes. Sunlight is roaring past McCandless in a torrent, enough energy to heat metal past boiling, and he cannot see a single particle of it unless it happens to land directly on his retina or on a surface he is looking at. Picture yourself standing where he stood. You are inside a flood of light, traveling in every direction at once, and the space around you is absolutely black. The light is there. Your eyes simply have no way to know. This is why you will never find a glowing beam in an authentic photograph taken in space. No shafts, no searchlight cones, no visible rays streaming from the sun. Nothing is out there to catch them, which creates something you have never experienced on Earth, an absolute shadow. In your room, light bounces. It hits the ceiling, the wall, the floor, and scatters back into every corner. Even the shadow under your bed receives light from somewhere. That is why shadows on Earth have soft edges and grey interiors. The room itself keeps filling them in. In vacuum, nothing fills anything in. The line between lit and unlit is a knife edge, and the far side of that edge is nothing. You can measure this in temperature. Without thermal control, the sunward skin of the International Space Station would climb to roughly 121 degrees Celsius, 250 degrees Fahrenheit, hot enough to boil water and keep it boiling. On the shadowed side, thermometers would fall to about minus 157 Celsius, minus 250 Fahrenheit. That is far colder than the coldest temperature ever recorded anywhere on the surface of our planet. A swing of 500 degrees Fahrenheit, and you can cross it by moving your hand a few centimeters. That knife edge has a consequence spacewalkers live with constantly. A tool that crosses from sunlight into shadow does not fade. It does not dim. It vanishes, instantly, completely, as though someone deleted it from the universe. There is no residual glow to trace, no faint outline against a background, because there is no background. So everything gets tethered. Every wrench, every bag, every camera, and every human being. Not primarily because objects float away, but because in that environment, an untethered object stops existing the moment it drifts into the dark. Every 90 minutes or so, an orbiting spacecraft passes into Earth's shadow, and for roughly 45 of those minutes, the crew is in genuine night. So the helmets carry lamps. Those lamps do not light the darkness. They cannot. There is nothing out there for the light to land on. What they create is a small bubble of visibility around the astronauts' hands and the surface directly in front of them. Inside that bubble, work is possible. 1 centimeter beyond it, nothing. In July of 2013, during a spacewalk outside the station, ESA astronaut Luca Parmitano found water pooling inside his helmet, drifting across his eyes and into his nose. Mission Control ordered him back to the airlock. As he turned to make the crossing, the station entered orbital night, and he could see nothing except the small patch his headlamps reached, which reframes something we tend to think of as ordinary. Exterior lighting on a spacecraft is not a convenience, the way a porch light is a convenience. It is a life support system. Take it away, and a trained astronaut in a functioning suit becomes a person who cannot locate their own vehicle. And low Earth orbit is the mild version. Imagine you could stand at a window somewhere in interstellar space, the enormous gulf between stars, with no star close enough to show a disk. You are safe, sealed, breathing. You turn out the cabin lights and look out. There is no gradient, no horizon line, no faint band where one thing becomes another, no texture, no motion, no near or far. Your visual system is built to extract edges and depth from structure, and it is receiving zero structure whatsoever. Not a dim image, an absent one. Raise your hand and touch your own face. You will feel your fingers land on your cheek and see absolutely nothing happen. Your hand, 6 inches from your eyes, remains completely invisible, and those rod cells, the ones capable of responding to a single particle of light, are sitting there, fully dark adapted, at maximum sensitivity, receiving nothing at all. The finest low-light detector evolution ever produced, waiting for a signal that never comes, like a smoke detector in a house with no air. That word, single, hides a genuine scientific fight, and it is worth sitting with because it tells you how close to the edge human vision really runs. Rod cells can respond to 1 photon. That much is established. What remains disputed is whether that response ever reaches conscious awareness, whether a person can actually notice 1 particle of light. In 2016, a team led by Jonathan Tinsley and Maxim Molotsov in the laboratory of Ali Pasha Vaziri published results in Nature Communications using a quantum light source that fires photons one at a time. Across more than 30,000 trials, with about 2,400 delivering a real single photon, observers identified the correct moment 51.6% of the time. Pure guessing would give 50. That is a coin coming up heads 516 times in 1,000 instead of 500. A hair above chance, but the team argued it was a real hair. The following year, Paul Kwiat's group at the University of Illinois at Urbana-Champaign published a direct response titled "Still No Evidence for Single Photon Detection by Humans." Their objection was not that the result felt wrong. Their objection was statistical. They argued the analysis was inappropriate and the experiment lacked the power to support the claim at all. The disagreement has never been settled. As it stands, we do not know with confidence whether a human being can consciously perceive 1 photon. But out there, past the window, in the dark between the stars, the argument becomes irrelevant. Whether the threshold is 1 photon or 10 does not matter when the number arriving is 0. We have the relationship backwards, all of us, and we have had it backwards our entire lives. We speak as though light is the normal state of the universe, and darkness is what happens when light is removed. A subtraction, an interruption, a failure of something that should be present. Your room goes dark because you flipped a switch. The night comes because the sun set. Darkness, in our experience, is always something that happened. but that experience was built inside a bubble, a lit planet wrapped in a glowing atmosphere, orbiting a star. Every human eye that has ever opened inside that bubble. Step outside it and the arithmetic reverses. Darkness is not the exception out there. Darkness is the default condition of almost the entire universe, and light is the rare, local, temporary event, the anomaly. We are not creatures who live in the light and occasionally experience dark. We are creatures who evolved inside one small illuminated pocket and mistook it for the way things are, which leaves one question standing, and it is the one everything else depends on. Why is it dark out there at all? Not why it looks dark. We have that answer now. Why is the universe built in a way that leaves almost all of it empty enough for the dark to exist in the first place? The answer begins with a number so small it barely qualifies as a number at all. That number is one atom, in a volume the size of a sugar cube. That, on average, is what interstellar space contains, the ordinary space between the stars of our own galaxy. To feel how strange that is, you need the comparison. Take that same sugar cube and fill it with the air in the room around you right now. At sea level, it holds roughly 27 quintillion molecules, a 27 followed by 18 zeros. If you tried to count them one per second, without sleeping, without stopping, you would need something like 800 billion years. The universe has only existed for about 13.8 billion. You would need roughly 60 universes worth of time to finish counting the air inside a sugar cube. Now remove all of it but one atom. That is the space between the stars. And go further out into intergalactic space, the enormous gulfs between whole galaxies, and the density collapses again. Out there, you need roughly a full cubic meter, a volume about the size of a washing machine, to find a single atom. Think about that for a moment. Not a cloud of gas, not a thin haze. One atom, alone, in a box you could climb inside. Now the objection that should be forming. Surely we can do better in a laboratory. We have vacuum pumps, cryogenics, decades of engineering. We cannot. Beneath the Swiss-French border, CERN operates the Large Hadron Collider, and its beam pipes hold the most rarefied artificial space human beings have ever created. After a thorough evacuation, those pipes still contain roughly 3 million molecules per cubic centimeter. 3 million. Against 1. The finest vacuum our civilization can manufacture, built with 250,000 welded joints and cryogenic pumping and 2 solid weeks of extraction, is still about 3 million times denser than the ordinary space between stars. We have never made anything as empty as the space just outside our own solar system, and we almost certainly never will. And that emptiness is the whole answer. Light needs something to strike before your eye can register it. Without particles in the way, a beam travels invisibly, and the space it crosses stays black. Space has no particles in the way, not enough to matter. A photon can travel for 1,000,000 years without encountering a single thing to bounce off. So it arrives at your eye, or it arrives nowhere, and everything in between stays absolutely dark. The universe has no smoke in it. That is the entire mechanism. But emptiness is not just a local condition. Once you follow it outward, the scale of it becomes difficult to hold in your head at all. The nearest star to our Sun is Proxima Centauri, and thanks to the European Space Agency's Gaia mission, we know its distance with remarkable precision. 4.2465 light-years, about 40 trillion kilometers, roughly 25 trillion miles. Numbers like that slide off the mind. So shrink everything. Imagine the Sun reduced to the size of a golf ball sitting in your palm. At that same scale, Earth becomes a grain of sand about 4.5 meters away, roughly 15 feet, the width of a small living room. Everything that has ever lived, every ocean, every city, every person you have ever loved, is on that grain of sand across the room. Now, where is the next star? Keep the same scale. Keep the golf ball in your hand. Proxima Centauri would be another small ball roughly 1,200 kilometers away. about 760 miles, farther than the drive from London to Vienna. 2 golf balls, 760 miles apart, and between them a scattering of individual atoms, so thinly spread that nothing you could build would ever notice them. That is not unusual. In our neighbourhood of the galaxy, based on current surveys of nearby stars, the average separation between one star and the next runs somewhere around 5 light years. Our situation is typical. The typical situation is nothing, which raises an obvious problem. If stars are that isolated, why does the night sky look so crowded? Because your eyes are performing a trick they cannot help performing. Under genuinely dark skies, the total number of stars visible to the unaided eye across the entire globe comes to about 9,000, according to careful magnitude counts. Only half the sky sits above you at any moment, so from one spot, in near-perfect conditions, you might see 4,000 or 5,000. From a suburb, a few hundred. From a city centre, a few dozen. But here is why they seem to press together. Your depth perception works by comparing the slightly different images from your 2 eyes, and that comparison fails completely past a few dozen meters. Beyond that, everything collapses onto a single flat surface. So the sky becomes a dome, and stars painted on a dome look adjacent. They are not adjacent. 2 stars that appear to be touching in the same constellation may be separated by more distance than either is from us. The night sky is not a field of lights. The night sky is a 2-dimensional lie told by a 3-dimensional void. Place yourself in that void for a moment. Imagine a sealed craft, halfway between our Sun and Proxima Centauri, about 2 light years from either. You look back toward home. The Sun is a point, a brilliant one, comparable to the brightest star in Earth's night sky, but a point all the same. No disk, no warmth on your face through the window. It throws no shadow you could ever detect. Everything you have ever known orbits that pinprick invisibly. Now turn away from it. In every other direction you find no horizon, no ground, no ceiling, no up, no down, no near, no far. Nothing moves, because nothing is close enough to appear to move. The only sense still reporting anything real is proprioception, the quiet internal awareness that tells you where your own arms and legs are without looking at them. That becomes your entire frame of reference. Your body is the only object left in the universe that you can locate, and that is the small gap. The one between 2 neighbouring stars. The gap between galaxies is a different order of thing entirely. Our Milky Way and the Andromeda Galaxy sit about 2.5 million light-years apart, and that expanse is emptier than anything inside either one. The light reaching your eye from Andromeda tonight, and you can see it with the naked eye, a faint smudge, if your sky is dark enough, left that galaxy roughly 2.5 million years ago. On Earth at that time, the earliest members of our own genus were chipping the first crude stone tools in East Africa. That light has been in transit ever since, crossing a desert with essentially nothing in it. Stand at the midpoint. From out there you would see exactly 2 things worth seeing. 2 faint spirals, one on either side, each small enough to cover with a thumbnail. In every other direction, nothing at all. Our sun would not be visible, not dim, not faint, unresolvable, swallowed into the general glow of a smear of light. Every empire, every war, every language, every song ever written sits inside that one soft patch, and no eye at that distance could ever separate it out. Pull back further, and something extraordinary appears. A structure nobody expected before the great galaxy surveys mapped it. Matter in the universe is not scattered evenly. It hangs in a vast connected network astronomers call the cosmic web. Dense knots where galaxy clusters sit, long filaments of galaxies strung between them like threads, flat sheets and walls joining the threads together. And in between, enormous hollows, voids. Picture the bubbles inside a risen loaf of bread. The dough is the filaments and walls. Every galaxy in existence lives in the dough. The bubbles are the voids. Now change the proportions until the bubbles dominate almost completely, because they do. Based on current mapping and simulations, Cosmic voids occupy roughly 80% of the volume of the universe, while containing only around 10% of its mass. Almost everything, by volume, is whole. The universe is not a place with gaps in it. The universe is a gap with places in it. In 1981, 4 astronomers found out exactly how large a single hole can be. Robert Kirshner, working with Augustus Umler, Paul Schechter, and Stephen Schechtman, was measuring redshifts, the stretching of light from receding galaxies, which converts a flat photograph of the sky into a genuine 3-dimensional map. They were mapping a patch of sky toward the constellation Boötes, and a gap opened in the map. Not a few missing dots. A hole. The Boötes void, sometimes called the Great Nothing, spans something in the region of 330 million light-years, with its center about 700 million light-years from Earth. In a volume that size, the average density of the cosmos predicts roughly 2,000 galaxies. Follow-up surveys have found around 60. To feel that distance, cross it at the speed of light. Starting now, you would arrive in roughly 330 million years. Run that backward on Earth, and 330 million years ago, the first great coal forests were spreading across a world that had not yet seen a dinosaur. Now, 2 honest complications. The size is disputed. Later remeasurements shrank the void considerably, and published diameters range from around 250 million light-years up to 330 million, depending on the survey and the assumptions used. The larger figure is the one usually quoted. The smaller ones are not fringe, and the origin remains unsettled. The leading explanation holds that the Boötes void formed when several smaller voids merged into one, a picture consistent with the 60 galaxies inside it, appearing to lie along tube-like structures as though marking old boundaries that dissolved. Consistent is not the same as demonstrated. No one has shown it happened. Astronomers have made one observation about it that is genuinely unsettling. Had our galaxy formed near the center of a void that size, our sky would have been so empty of neighbors that we might not have discovered other galaxies existed until deep into the 20th century. Our entire picture of the cosmos depends partly on where we happen to be standing. We may be standing in one. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie published evidence that the local universe, out to a scale of about 300 megaparsecs, roughly a billion light-years in every direction, contains noticeably fewer galaxies than the cosmic average. The region has become known as the KBC void, or simply the local hole, 2 billion light-years across, and we may be inside it. The stakes are higher than they sound because of a problem cosmologists call the Hubble tension. Measurements of how fast the universe is expanding disagree depending on whether you measure the early universe or the nearby one. If we sit inside an underdense region, matter would drain outward toward the denser walls around us, and that outflow could make our local expansion look faster than it truly is. A void could be faking the whole discrepancy. In 2020, Moritz Hasselbauer, Indranil Banik, and Pavel Krupa argued the observed void is deep enough and wide enough to account for the tension entirely. But a 2025 analysis, fitting direct distance measurements to galaxies rather than redshift counts, found the velocity data prefer a void far smaller, on the order of 10% of the size the earlier work required. Both sides are measuring real things. The disagreement is live and honest and unresolved. The local hole has company. The Eridanus supervoid, confirmed through gravitational lensing using dark energy survey data in 2021, stretches roughly 1.8 billion light-years and sits aligned with the coldest patch in the cosmic microwave background, though it does not fully account for that cold spot. And the giant void in Canes Venatici, found in 1988, runs somewhere between 1 and 1.3 billion light-years across. The holes are the largest things we have ever found. One distinction has to be made here, because the sky contains a second kind of blackness that looks identical and is not. About 400 to 500 light-years away, in the direction of Ophiuchus sits a small object called Barnard 68. Photograph it, and you see a hole, a perfectly black, sharply edged patch where the crowded star field simply stops. Nothing is missing there. Barnard 68 is a Bock globule, a cold, dense knot of gas and dust roughly half a light year across, chilled to about 16 degrees above absolute zero. It is not an absence of stars. It is a curtain in front of them. Dust does not delete starlight. It dims it, and it reddens it, scattering blue wavelengths more strongly than red. The same physics turns your sunset orange. Air scatters the blue out of low sunlight, and what survives the journey to your eye is red. Interstellar dust does exactly that, over light years instead of miles. And when astronomers pointed infrared instruments at Barnard 68, longer wavelengths slipped straight through the dust and revealed thousands of background stars that visible light could never show. The stars were there the whole time, so the sky holds two darknesses. One is a curtain, the other is a room with nothing in it. They can look the same from here, and telling them apart has taken us a century. Here is what makes all of this stranger, rather than simply bleaker. We tend to treat the void as leftover, the unused space between the parts that matter. That reading has it backwards. Voids are not what remains after structure forms. Voids are what forming structure produces. Slightly underdense regions in the early universe lost their matter to slightly overdense ones, gravity pulling material out of the hollows and into the walls, deepening the emptiness with every passing billion years. The holes are still growing, and without them, none of this exists. Discrete objects, stars, planets, galaxies, require separation. If matter were spread evenly and densely everywhere, gravity would have collapsed the whole arrangement into something with no structure and no observers in it. Every star burns in its own private isolation, because the isolation is what allowed it to become a star. The void is not the background of the story. The void is the story. Everything we call an object is a rare defect in it, and yet something in that account does not add up, and it should be bothering you already. Space is nearly empty, yes, but it is not infinitely empty of stars. Look in any direction on a clear night and you find them. Thousands, then billions once you add a telescope, scattered through a cosmos that may extend forever. So, follow the logic. If stars fill an unbounded universe, then every single line of sight you could ever draw, extended far enough, should eventually land on the burning surface of one. Every point on the sky should be as bright as the face of the sun. The night should be blinding. It is not. And for 200 years, that single fact, the plain blackness between the stars, has been one of the most quietly devastating clues in all of physics. Walk into a forest and look straight ahead. Close to you, gaps open between the trunks. You can see through. But keep walking, and something happens. The trees behind the trees fill in the gaps. The trees behind those fill in what remains. Go deep enough into a large enough forest, and every direction you turn ends in bark. No line of sight escapes. Now put stars in place of trees, and the universe in place of the forest. If the cosmos runs on forever, filled evenly with stars, then every straight line you could draw from your eye must eventually strike the surface of one. Not most lines. Every line. And here is the part that closes the trap. A star's surface does not get dimmer with distance in the way you might assume. Move a star 10 times farther away, and its light does fade, but its apparent size shrinks by exactly the same factor. Brightness per patch of sky stays constant. You know this already from an ordinary white wall. It looks equally bright whether you stand beside it or across the room. The wall does not dim, it only gets smaller. Follow that through, and the sky should not merely be bright. Every point on it should burn at the surface temperature of a star. Day and night should be indistinguishable, and both should be lethal. Instead, you can go outside tonight and look into black. That contradiction has a name, and it was earned slowly. Johannes Kepler raised it in 1610 in a letter responding to Galileo's first telescope observations, and he treated the darkness as proof the universe must be finite, walled, bounded, containing only so many stars. Edmond Halley picked it up around 1720. Jean-Philippe Loy de Chezeaux gave it real mathematical shape in 1744, and in 1823 the German physician and amateur astronomer Heinrich Wilhelm Olbers published an essay on the transparency of space that made the problem famous. His name stuck to it. Olbers' paradox, sometimes called the dark night sky paradox. He was not the first to notice it, and his own explanation failed, but the label survived. Their proposed answers all collapsed. Halley suggested distant starlight simply faded to nothing past some limit, which is not how light behaves. De Chezeaux and Olbers both reached for dust, clouds of material between the stars, absorbing the excess light before it reaches us. John Herschel dismantled that one with a single thermodynamic observation. Dust that absorbs light heats up. Heat it long enough in an eternal universe, and it glows as fiercely as what it was blocking. You cannot hide a fire behind a curtain forever. Eventually the curtain burns. 3 centuries of intelligent people, and the blackest, most obvious feature of the night sky stayed unexplained. The first person to reach for the right idea was not an astronomer. In 1848, Edgar Allan Poe published Eureka, a strange, sprawling prose poem about the material and spiritual universe that most of his contemporaries ignored. In it, he proposed that the distances involved are so vast that light from the most remote regions has not had time to arrive yet, that we see darkness in those directions because nothing has reached us from them. He had no equations. He had no evidence. He wrote it as literature a year before he died, and it happens to contain the outline of the answer. That answer has 2 halves, and only one of them was available to him. Light moves at 299,792 kilometers every second, about 186,282 miles, fast enough to circle Earth roughly 7.5 times while you finish this sentence. But in cosmic terms, it is painfully slow. The universe, according to the final analysis from the European Space Agency's Planck mission, is about 13.8 billion years old, which means light has had 13.8 billion years to travel, and not 1 second more. Anything farther away than that light could reach is not dim, it is simply not here. Cosmologists call that boundary the particle horizon. Not a wall, nothing is out there stopping anything, just a limit imposed by the clock. Now the strange part. You might expect that boundary to sit 13.8 billion light-years away. It does not. The observable universe measures roughly 93 billion light-years across, about 46.5 billion in every direction. Picture an ant crawling along a rubber band toward your hand. It starts 10 centimeters away, about 4 inches. While it crawls, you stretch the band. The ant arrives, but the spot where it began is now far more than 10 centimeters behind it. The journey was completed. The distance grew anyway. Space did that to every photon in transit. The light arrived. The galaxies that emitted it are now 3 times farther away than the distance the light actually crossed. So the forest is not endless after all. Most of the trees have not shown up yet. The second half of the answer is stranger, and Poe never touched it. Space does not merely expand between galaxies. Space stretches the light itself while it travels. A wave leaves a distant galaxy at one length and arrives at your telescope longer, pulled out like a coiled spring drawn between 2 hands. Astronomers call it redshift because visible light stretched slightly becomes redder. Stretch it enough and it stops being visible at all. It slides past red into infrared and past infrared into microwave, which means Olbers was not wrong. The blazing sky he described exists. It is out there, right now, filling every direction you could point. Light from the earliest luminous era of the universe, stretched by billions of years of expansion until it fell entirely out of the range your eyes can register. We detect it constantly. We call it the cosmic microwave background. Its temperature is 2.725 Kelvin, under 3 degrees above absolute zero, the coldest temperature physically permitted. In everyday terms, roughly minus 270 degrees Celsius, minus 455 Fahrenheit. A glow in every direction, uniform to within one part in 100,000, and utterly invisible. And here is what almost nobody appreciates about the blackness overhead. A dark night sky is direct observational evidence that the universe had a beginning, not a theory about it. Evidence for it, available to anyone who steps outside. For centuries the proof was hanging above every human head, and nobody could read it. But that raises a question the old astronomers could never have asked. How dark is dark? Not poetically, numerically. Measuring the true darkness of space turns out to be almost impossible from where we live. Our solar system is full of dust, fine grains spread through the plane of the planets, catching sunlight and scattering it into a faint haze called zodiacal light. From Earth orbit, even from the Hubble Space Telescope, that haze swamps everything fainter behind it. Imagine trying to judge how dark a field is at midnight, while someone holds a lit phone 6 inches from your face. You are not measuring the field, you are measuring the phone, so the measurement had to be made from somewhere else. After its encounter with Pluto, NASA's New Horizons spacecraft kept going, out to 42 and 45 times Earth's distance from the Sun, far enough that the dust haze thins to almost nothing. Using its long-range reconnaissance imager, or LORRI, the team measured the raw brightness of empty sky. The result, roughly 10 times darker than the darkest sky the Hubble Space Telescope can access. Not a marginal improvement, an entirely different regime of darkness, reachable only by leaving. What they were hunting is called the cosmic optical background, the summed light of every star in every galaxy that has ever shone, arriving from all directions as one faint, featureless glow. Add up cosmic history, and this is the residue. In 2022, Todd Lauer and colleagues published the analysis of a test field. They detected the background clearly, and when they compared it against the light expected from all known galaxies, only about half the signal was accounted for. The other half had no source. Statistically, the leftover component sat around 4 sigma, roughly a 1 in 15,000 chance of being random noise. Not proof, but far too strong to wave away. Consider what an unexplained glow would mean. Either the universe contains a population of faint galaxies we have entirely missed, or something else out there emits visible light that our physics has not accounted for. Decaying particles, unknown structures, something. Then came the correction. In 2024, Mark Postman, Todd Lauer and their collaborators published a far larger survey. 16 carefully chosen fields at high galactic latitude, selected specifically to minimize contamination. And crucially, they used far infrared data from Planck to calibrate exactly how much scattered Milky Way light was leaking into the images. That technique had not existed for the earlier work, and it revealed the problem. The amount of dust-scattered light from our own galaxy had been underestimated. Correct for it properly, and the excess vanishes. The remaining glow matches the light produced by all galaxies over roughly the past 12.5 billion years. No more. Lauer's summary was blunt. Look outside the galaxies, and you find darkness and nothing further. The earlier result was not carelessness. Measuring this background means subtracting foregrounds far brighter than the thing you are looking for, like weighing a single envelope by weighing the truck twice, with and without it. Get the truck slightly wrong, and the envelope seems to weigh a kilogram. The current evidence points clearly toward galaxies alone. Whether it holds as instruments improve is a question the data has not finished answering. And now the part of this that genuinely disturbs cosmologists. The particle horizon marks what has reached us. A second boundary marks whatever can. Beyond a distance of roughly 16 billion light-years, space between us and those galaxies is being added faster than light can cross it. Light leaving them today is not slowed, not blocked, not weakened. It simply never closes the gap. Every second it advances, more distance appears behind it than it covered. Picture sprinting up a down escalator that keeps accelerating. Your legs work perfectly, you still lose ground. Those galaxies exist. They are burning right now. They will never be seen by anything in this galaxy, ever, under any technology. And as expansion continues, more of them cross that line and disappear from the reachable universe, quietly, permanently, one by one. In 2007, Lawrence Krauss and Robert Scherer followed that logic to its end, and the conclusion is unsettling in a way that has nothing to do with fear. Extrapolate forward. Around 100 billion years from now, the cosmic microwave background will have been stretched to wavelengths near a meter and dimmed by about 12 orders of magnitude, 1 trillion times fainter, undetectable. Every galaxy outside our own gravitationally bound group will have receded beyond visibility. What remains is one island of stars in an otherwise featureless dark. Astronomers living then will build telescopes. They will observe carefully. They will find a single galaxy, a static sky, and no evidence whatsoever of expansion, of a beginning, of a Big Bang. And every measurement they can possibly make will support that conclusion. They will be rigorous, they will be honest, and they will be wrong with no way of knowing it, which puts our own moment in a strange light. We are not living in a typical era of cosmic history. We are living in the narrow window when the evidence still exists, when the background glow is still detectable, when distant galaxies are still visible, when the fossil record of the universe's birth has not yet faded past reading. That window is closing, slowly, but it is closing. Darkness, then, is not the absence of light. Darkness is arithmetic, the arithmetic of how fast light moves, how long the universe has existed, and how much space keeps inserting itself in between. But notice what has quietly happened across all of this. Every answer so far has defined darkness by what our eyes can register. The sky is black because the light has not arrived, or because expansion pushed it out of the range our retinas respond to. The cosmic microwave background is invisible not because it is faint, but because it is the wrong color for us. That should stop you, because if a sky ablaze in every direction can look like nothing at all, then the word dark is not describing the universe. It is describing an instrument, and that instrument is sitting behind your eyes. The visible spectrum, everything you have ever seen, every color that has ever existed for you, occupies less than a single octave out of more than 60 in the electromagnetic spectrum, which raises the question this whole story has been circling from the beginning. If we can only see one narrow band, what exactly is out there in the rest of it? Almost everything. Think about what an octave actually means. In music, an octave is a doubling, the same note twice the frequency. Light works the same way. Double a wavelength, and you have climbed one octave up the electromagnetic spectrum. Now, count. From the shortest gamma rays to the longest radio waves, the spectrum spans more than 60 octaves. Your eyes respond to wavelengths between roughly 380 and 700 nanometers, a nanometer being a billionth of a meter, so small that a single human hair is about 80,000 of them across. 700 is not even double 380. Every color you have ever seen, every sunset, every face, every photograph, all of it fits inside less than one octave out of more than 60. Imagine a piano stretching the length of a city block, and you can hear the notes between two adjacent keys. That is human vision, and the reason for that narrowness is not arbitrary. Our eyes evolved to catch the wavelengths the sun produces most abundantly, and, just as importantly, the wavelengths that pass cleanly through Earth's atmosphere to reach the ground. Evolution built a detector tuned to the one channel that was both loud and unblocked. Everything else got ignored, because nothing on Earth ever needed it. So when we say space is dark, we are not describing space. We are reporting a limitation. Move slightly beyond red, into infrared, longer wavelengths, The range we experience as radiant heat rather than sight. Point a telescope there, and something remarkable happens. The James Webb Space Telescope was built almost entirely for this band, and the reason is expansion. Light from the earliest galaxies has been stretched so far by its journey that it arrives in the infrared. To an optical telescope, those galaxies do not look faint. They look absent. JWST sees them clearly for one reason. It is listening on the right frequency. Go longer still, into radio. Pulsars, the spinning corpses of dead stars, broadcast pulses so regular they were briefly mistaken for signals. Quasars blaze from the centers of distant galaxies. Natural masseurs beam concentrated microwave light from clouds of gas. And these long wavelengths do something visible light cannot. They pass straight through interstellar dust. You know this effect already. Stand outside a room where music is playing, and you hear the bass thumping through the wall while the melody disappears. Long waves pass through obstacles. Short waves get absorbed and scattered. Interstellar dust does exactly that to starlight, blocking the short visible wavelengths while radio waves sail through untouched. Entire regions of our galaxy that appear as black holes in the sky are, in radio, wide open. Now go the other direction, shorter than violet, into ultraviolet, X-rays, and gamma rays. This sky belongs almost entirely to violence, matter spiraling into black holes, heated to millions of degrees before it falls. Jets fired from galactic cores, neutron stars, supernova remnants, objects that are dying, or feeding, or both. The same sky. 5 completely different universes, depending on which band you open. And light is only part of what is passing through. Right now, as you sit reading this, roughly 100 trillion neutrinos are moving through your body every second. Ghostly particles with almost no mass, no electric charge, produced mostly by nuclear fusion in the core of the Sun, about 65 billion of them crossing every square centimetre of your skin, every second, day and night. The Earth does not stop them. At midnight, they are coming up through the floor, having passed through the entire planet on the way. They do not interact with you, not because they are avoiding you, because you are, from their perspective, essentially not there. By most estimates, across an entire 80-year human lifetime, about 1 neutrino will actually collide with an atom in your body. 1, out of a number so large it has no useful name. You are transparent, and you never noticed. And somewhere inside that flood sits something we have never touched. Theory predicts a cosmic neutrino background. Relic neutrinos released roughly 1 second after the Big Bang, not 380,000 years after, like the microwave background. 1 second. They would be the oldest thing in existence that could ever be detected. They are almost certainly streaming through this room. And their energies today are so vanishingly small that no existing experiment can see them, and no proposed experiment reliably can either. We know they are there because the universe does not work without them. We have never directly detected a single one. Which brings us to the number this entire story has been walking toward. Take everything you have ever seen, every star, every galaxy, every planet, every nebula in every photograph ever published. Add everything you have ever touched, this device, your own body, the air in your lungs, the ground under the building. Add every atom in every instrument humanity has ever built. Based on the final Planck results, all of that together comes to about 4.9% of what the universe contains. Roughly 27% is dark matter. Roughly 68% is dark energy. And neither one has ever been seen. Not because they are faint, but because they do not interact with light at all. Think about that for a moment. Every telescope, every camera, every eye that has ever opened, across every wavelength we can access. Collectively, we have observed about 1/20th of the contents of reality. The evidence for dark matter is not a hunch. It arrives from 4 independent directions, and they agree. In the 1970s, Vera Rubin measured how fast stars orbit at different distances from the centers of galaxies. In the solar system, outer planets move slower than inner ones. Neptune crawls, Mercury races, exactly as gravity dictates. Rubin found galaxies behave nothing like that. Stars at the outer edges move just as fast as stars near the middle. Picture a merry-go-round where the horses on the outer rim swing around as quickly as the ones at the center. The only way that happens is if something you cannot see is holding the whole structure together. Second, gravitational lensing. Mass bends light, so a massive object distorts the images of galaxies behind it, like looking through the base of a wine glass. Measure the distortion, and you can weigh what is in front. Consistently, the weight exceeds everything visible. Third, and most striking, the bullet cluster. Two galaxy clusters collided. The hot gas, which holds most of the ordinary matter, slowed down and piled up in the middle, exactly as gas should. But when astronomers mapped the mass through lensing, the bulk of it had sailed straight through the collision and out the other side, leaving the ordinary matter behind. The visible material and the gravitational material physically separated. And fourth, the precise pattern of ripples in the cosmic microwave background only fits if dark matter was present in the early universe, in roughly the amount we infer today. 4 methods, 4 different eras and scales, one answer. Here is where the story cracks open. Dark matter emits nothing, absorbs nothing, reflects nothing, at any wavelength, in any band, to any instrument. Not dim, not obscured. Transparent to the entire spectrum, top to bottom, which leaves an obvious alternative that some physicists take seriously. Instead of adding invisible mass, what if gravity itself behaves differently than we think at very low accelerations? That idea, proposed by Mordechai Milgram in 1983, is called Modified Newtonian Dynamics, or MOND, and it has a real strength. With a single adjusted parameter, it predicts the rotation of individual galaxies with striking accuracy, in some cases better than dark matter models do. Its weaknesses are equally real. MOND struggles badly with galaxy clusters, has no clean explanation for the bullet cluster's separated mass, and does not naturally reproduce the cosmic microwave background pattern. The strong majority of cosmologists favor particle dark matter, except we have not found the particle. Nearly a mile beneath South Dakota, at the Sanford Underground Research Facility, the Lux Zeppelin experiment operates the most sensitive dark matter detector ever built. 7 metric tons of liquid xenon, shielded from cosmic rays by solid rock. In December of 2025, the collaboration reported 417 live days of data collected between March 2023 and April 2025. The largest data set any dark matter experiment has ever gathered. No detection. That result does not disprove anything. It narrows the hiding places, which, as one physicist put it, is genuine information. But 4 decades of increasingly sensitive experiments have now returned the same answer, and the space left for the leading candidate keeps shrinking. Dark energy is stranger still, and we found it by accident. In 1998, 2 competing teams, one led by Saul Perlmutter, the other including Brian Schmidt and Adam Rees, were measuring distant exploding stars called Type 1a supernovae. These explode with a consistent intrinsic brightness, which makes them usable as distance markers. The dimmer one appears, the farther away it must be. Both teams expected to measure how much cosmic expansion had slowed under gravity. Instead, the distant supernova came back dimmer than any deceleration model allowed, farther away than they should have been. The expansion was not slowing, the expansion was speeding up. That discovery earned the Nobel Prize in 2011 and handed physics a component that makes up more than 2/3 of everything, a property of space itself that pushes it apart, growing more dominant as the universe grows emptier. And whether it is truly constant is now, for the first time, genuinely in question. On March 19, 2025, the Dark Energy Spectroscopic Instrument released results from more than 14 million galaxies and quasars gathered over 3 years. Combined with the microwave background, weak lensing, and supernova data, the results show a preference for dark energy that changes over time rather than staying fixed, at a statistical significance ranging from 2.8 up to 4.2 sigma, depending on which supernova catalogue is used. Sigma measures how unlikely a result is to be a fluke. 3 sigma means roughly a 3 in 1,000 chance of coming from noise alone. 5 sigma is the threshold physics accepts as discovery. 4.2 is not 5, and the history of physics contains a long list of 3 sigma results that evaporated with better data. The DESI team is careful about this, and so are their critics. Much of the strength depends on supernova calibration still being refined, but consider what hangs on it. If dark energy is weakening rather than constant, the entire far future of the universe, how cold it gets, how dark it gets, whether expansion continues forever, would need rewriting. Descend now to the smallest scale, and the pattern repeats. Empty space is not empty. Quantum field theory describes the vacuum as restless, particle pairs flickering into existence and annihilating faster than any instrument could isolate them. Not a metaphor, a measurable effect. Hendrik Casimir predicted the test in 1948. Place 2 uncharged metal plates extremely close together in a vacuum, and they will be pushed toward each other, because fewer quantum fluctuations fit in the narrow gap than exist outside it. Sailors have known the shape of this for centuries. 2 ships riding side by side in a choppy swell get drawn together, because the water between them is calmer than the waves striking their outer hulls. The pressure imbalance does the rest. Steve Lamoureux measured the Casimir version of that force in 1997. The vacuum pushes, which raises an obvious thought. If empty space carries energy, perhaps that energy is dark energy. The calculation is a catastrophe. Sum the 0-point energies of the known quantum fields, and the predicted energy density of the vacuum exceeds the observed value by something in the region of 120 orders of magnitude. A gap so large that the comparison barely functions, like calculating that an object should weigh 5 pounds and finding it weighs 5 followed by 120 zeros. One widely used textbook calls it probably the worst theoretical prediction in the history of physics, and even the size of the failure is contested. Depending on where you cut off the calculation and what assumptions you make, published estimates of the mismatch run anywhere from about 50 orders of magnitude to 120. Jérôme Martin's 2012 assessment landed near 55. Physicists cannot agree on how wrong they are. Add one more crack. Measure the expansion rate of the universe using the early universe microwave background, and you get about 67 kilometers per second per megaparsec. Measure it using nearby supernovae and Cepheid stars, and you get about 73, roughly 8% apart, with errors of 1% or less on each side. The Hubble tension. 2 rigorous methods, both refusing to move. Step back and look at what has accumulated. 95% of the universe's contents, invisible to every eye and every camera we possess. A vacuum that theory describes with the largest error in the history of science. 2 measurements of the same expansion that will not reconcile. A background of relic particles from 1 second after the beginning, streaming through your body, permanently undetected. And a word, dark, that we have been using this entire time, as though it described the cosmos. It does not. It describes us. It describes a retina tuned to one narrow band because that band happened to reach the surface of one planet, and a species that built its entire vocabulary of presence and absence around what that retina could report, which is why every telescope now under construction is, in a sense, an argument. The Vera C. Rubin Observatory, surveying the entire southern sky repeatedly. The Nancy Grace Roman Space Telescope, mapping dark energy's behavior across cosmic time. Euclid, already returning data. Each one exists because someone was unwilling to accept that an empty-looking region is actually empty. And every single time we have built a new kind of eye, the dark has turned out to be full. We do not call it darkness because nothing is there. We call it darkness because we are the ones who cannot see. But that reframe has a limit, and honesty requires naming it. Because if darkness is only ever a statement about our instruments, then nothing in the universe is truly black. Everything is simply broadcasting on a channel we have not tuned into yet. That is not quite true. Some objects out there return almost nothing. Not to our eyes, not to our infrared detectors, not to any instrument at any wavelength. Surfaces darker than charcoal, darker than the blackest paint ever manufactured. Places that have not received a single ray of direct sunlight in billions of years. And at the extreme end, regions where light does not fail to escape because we lack the right sensor, but because escape itself is not permitted. Real black, physically measurably black, and the darkest of them is far closer to home than you would expect. Astronomers have a single number for this, and once you know it, the solar system rearranges itself. Albedo, the fraction of light a surface sends back. A perfect mirror would score 1. Everything returned. Fresh snow lands around 8/10, which is why a sunlit snowfield hurts to look at. Charcoal sits at about 4%, meaning 96% of the light striking it never comes back out. Earth returns roughly 30% of the sunlight that reaches it. Clouds, ice, ocean glare, nearly a third bounce straight back to space. Now, consider the moon. The full moon can light a path well enough to walk by. It looks brilliant, almost white, and it feels like the second brightest thing in the sky because it is. Its albedo is about 12%. Think about that for a second. The most luminous object in your night sky is made of material roughly as reflective as worn asphalt. A parking lot, hanging in the sky, lit by the sun. What makes it look white is not brightness at all, it is contrast. Put a dark grey rock against a perfectly black background, and your eyes will call it dazzling, which is the first hint of how badly our intuitions handle darkness. And the solar system contains things far, far darker than that. On September 22nd, 2001, NASA's Deep Space One spacecraft flew past a comet called 19P Borrelly, passing within 2,171 kilometers, about 1,350 miles, roughly the distance from London to Rome. The flyby was never part of the original mission. Deep Space One had already completed its job testing new technologies, and the comet encounter was a bonus. What it found was the darkest surface ever measured in the solar system. Borrelly's nucleus, a lump of ice and dust about 8 kilometers long by 3 across, or 5 miles by 2, has a geometric albedo of about 2.9%. Its bond albedo, the total fraction of energy it reflects across all angles, came in at 0.9%, lower than any object in the solar system that has ever been measured. The scientists at JPL reached for the most ordinary comparison they could find. The surface, they said, is about as dark as a blot of photocopier toner, and the reason for that blackness carries a quiet horror of its own. Comets are dirty ice. Each time one swings near the sun, heat drives the volatile compounds off as gas, and what remains behind is a crust of heavy, long-chain organic molecules, the tar-like residue at the bottom of the barrel. Dark material. Then the process turns on itself. A darker surface absorbs more sunlight. More absorbed sunlight means more heating. More heating drives off more volatiles, leaving more residue, darkening the surface further. The comet is not dark by accident. The comet is darkening itself, a little more with every orbit, and the darkness is what powers the process. Once it begins, nothing stops it. Halley's nucleus, imaged by the European Giotto probe in 1986, reflects about 4%, darker than coal. And cometary nuclei generally fall somewhere between 3 and 7%. The most spectacular objects in the sky, the ones that grow tails visible across continents, are built around some of the blackest cores in existence. Asteroids run just as dark, and this one has consequences. On June 27, 1997, NASA's Near spacecraft flew past asteroid 253 Matilda, a battered, crater-scarred body about 52 kilometers across, roughly 33 miles, the length of a marathon. Matilda reflects 3% of the sunlight that reaches it. NASA's own description at the time put it plainly: twice as dark as a chunk of charcoal, and the sample return missions confirmed the pattern up close. Japan's Hayabusa 2 measured asteroid Ryugu's surface at about 4%. NASA's OSIRIS-REx found Bennu averaging around 4.4%, with the darkest boulders near 3. Both spacecraft brought material home, and both sets of samples match the darkest asteroid classes we know. Here is the problem. We find asteroids by watching for moving points of reflected sunlight. An object returning 3% is not faint. It is close to optically invisible until it is close. The most primitive, carbon-rich bodies in the solar system, which are also the most numerous class of them, are precisely the ones hardest to detect. That is a live planetary defense problem, not a theoretical one. Every catalogue we build is biased toward the objects that shine, but the same physics that hides them also exposes them. A surface absorbing 97% of the sunlight hitting it does not destroy that energy. It re-radiates it as heat, which means the blackest asteroids, invisible to optical telescopes, glow brightly in infrared. Whole survey missions exist for exactly this reason, to find the things that cannot be seen by looking. Point the wrong instrument, and they are not there at all. And then, recently, something in the catalogue stopped adding up. In 2023, a team led by Daryl Seligman, working with Davide Farnocchia at JPL and others, reported a handful of near-Earth objects behaving impossibly. They looked like asteroids: bare rock, no coma, no tail, nothing in even the deepest stacked telescope images. But their orbits showed accelerations that gravity alone could not produce, and that sunlight pressure was far too weak to explain. They moved like comets. They looked like nothing. By December of 2024, the count had reached 14, published in the Proceedings of the National Academy of Sciences, and they sorted into 2 distinct families: an outer population, roughly a mile, about 1.5 kilometers, across, on long elliptical orbits, and an inner population, far smaller, closer to 1,000 feet or 300 meters, on nearly circular paths near Earth. Astronomers now call them dark comets. The leading explanation holds that they outgas water like ordinary comets, but produce so little dust that no tail ever becomes visible. That would explain the acceleration and the absence together, except no one has confirmed it. For years, the defining feature of these objects was the thing nobody could see. Then very recently, deep imaging of one near-Earth object, 1998 SH2, turned up a faint tail after all, confirming genuine cometary activity in at least that case, and suggesting more objects currently filed as asteroids may be quietly active. One confirmed case is not 14. The category remains open and the mechanism unproven, but the direction the evidence is moving is worth watching. Now come closer to home, closer than the asteroid belt, closer than any comet. The Moon's axis is tilted only about 1.5 degrees, which means that at its poles the Sun never climbs far above the horizon. Skim it sideways across a cratered landscape, and the floors of deep craters simply never receive direct sunlight. Not at noon, not in summer, not ever. Astronomers call them permanently shadowed regions, and some of them have been dark for over 1 billion years. Shackleton Crater, sitting almost exactly on the lunar south pole, formed in an impact around 3.6 billion years ago. Its interior has been in shadow since. Life on Earth was single-celled when the lights went out in there. The temperatures follow. NASA's Diviner instrument aboard the Lunar Reconnaissance Orbiter measures these crater floors at below -170 degrees Celsius, around -280 Fahrenheit, with isolated spots reaching -250 Celsius, -420 Fahrenheit. That is colder than the surface of Pluto, 6 billion kilometers further from the Sun. It is roughly 80 degrees Celsius colder than the coldest temperature ever recorded on Earth, on the East Antarctic Plateau, and it sits about 23 degrees above absolute zero, the floor beneath which nothing in this universe can go, which makes these craters perfect traps. Any water molecule that wanders in cannot escape. It freezes on contact and stays. Based on radar and neutron measurements from Chandrayaan-1 and the Lunar Reconnaissance Orbiter, scientists estimate the lunar poles hold at least 600 billion kilograms of water ice, enough to fill roughly 240,000 Olympic swimming pools. The most valuable resource on the Moon sits in the one place on the Moon you cannot see into, so we built a camera for it. ShadowCam, flying aboard South Korea's Danuri orbiter, is about 200 times more light-sensitive than the cameras normally used to map the lunar surface, resolving detail down to roughly 1.7 meters, about 5.5 feet, per pixel, and it takes its pictures using nothing but leftovers. Sunlight bouncing off a crater rim into the shadow below. Earthshine, sunlight that hit our planet, reflected off our oceans and clouds, crossed 380,000 kilometers and arrived on a crater floor about 10 times fainter than the scattered light already there. Imagine standing on that floor. Your feet rest on a regolith that has not been warmed by direct sunlight since before anything on Earth had a nucleus. Above you, sunlit peaks glow along the crater rim like a ring of distant lamps, throwing barely enough light to suggest the ground. And if you are near the right pole, Earth sits low and blue on the horizon, the brightest thing in your sky and the only reason you can see your own boots. Artemis is going to these regions. Faustini Crater, 41 kilometers wide, about 25 miles, contains the third largest permanently shadowed region on the Moon, and it overlaps one of the candidate landing zones. The resource and the blindness occupy exactly the same coordinates. Go further in, lava tubes beneath the lunar surface, caves, hollows inside small bodies, places where no photon has ever arrived from any source at any wavelength since the object formed. Put a human being inside one, and something strange remains true. You would still be producing light. Living cells emit photons, a real, measurable phenomenon called ultra-weak photon emission, sometimes called biophoton emission. It comes from oxidative metabolism. Reactive oxygen species generated in your mitochondria produce excited molecules that shed energy as light. Researchers have imaged it from human bodies using cryogenic cameras sensitive enough to count single photons, and found that the emission follows a daily rhythm, rising and falling with metabolic activity. A 2025 study imaging living and dead mice found the glow stops when the animal does. You are faintly luminous. Right now, what that light means is genuinely disputed. The German physicist Fritz Albert Popp, working in the 1970s and 80s, coined the term biophoton and argued the emission plays an active role in cellular communication, a claim that drew both interest and heavy criticism. The mainstream position treats it as a byproduct, real light, produced incidentally, carrying no message. Recent work has begun exploring whether it correlates usefully with disease states, but a diagnostic signal is not the same as a functional one, and in any case, it does not help you. The intensity runs about 1,000 times below the threshold of the human eye, so you would stand in that cave, emitting photons continuously in complete darkness, unable to detect a single one of them. Everything so far has been a matter of degree. 2.9% instead of 30. A crater instead of a plane. One class of object breaks the scale entirely. A black hole's event horizon is not a surface. Nothing is there to touch. No shell, no wall, no material. The horizon is a boundary in causality, the last place from which a signal can still climb out. Cross it, and every path forward in time leads inward. Not because escape is difficult, because outward stops being a direction that exists for you. Just outside sits the photon sphere, where gravity bends space-time so severely that light can orbit, traveling in a circle, coming back to where it started. Stand there, in theory, and you could see the back of your own head. In 2019, the Event Horizon Telescope released the first image of the supermassive black hole at the center of the galaxy M87. 3 years later, in 2022, they released Sagittarius A star, the one at the center of our own galaxy. But look closely at what those images actually show. Not the black hole. A black hole cannot be imaged. What you see is a shadow, a dark central region where light has been swallowed or bent away, outlined by a bright ring of radiation that passed close enough to be curved but not close enough to be captured. We photographed an absence defined entirely by what surrounds it, and the physics of what happens inside remains formally unresolved. In 1976, Stephen Hawking argued that black holes radiate, slowly evaporating, and that the radiation carries no information about whatever fell in. If true, information is destroyed, which quantum mechanics forbids. Around 2019 and 20, calculations involving what physicists call the Page curve and replica wormholes suggested a way out. The information does come back, encoded in the radiation. That work is elegant, widely respected, and has become the leading framework. But it operates in idealized model spacetimes, not the universe we live in, and extending it remains an open problem. Hawking radiation itself has never been observed. The firewall debate over whether an infalling observer meets a wall of violent energy at the horizon has not closed. As of now, the deepest question about the darkest object remains genuinely open, which brings the whole thing back to a laboratory bench. In 2014, the British company Surrey Nanosystems announced Vanta Black, a coating of vertically aligned carbon nanotubes that absorbs up to 99.965% of visible light. Light enters the nanotube forest, bounces between filaments, and is eventually absorbed and dissipated as heat rather than escaping. Objects coated in it lose their contours entirely. A crumpled sheet looks flat. A three-dimensional shape becomes a hole. 5 years later, a team at MIT led by Brian Wardle grew nanotubes on chlorine-etched aluminium foil and did better, 99.995%, about 10 times darker. They coated a $2 million diamond with it as an artwork, and the gemstone vanished into a void. That is the outer limit of what human engineering has achieved, and it is still not black. 5 parts in 100,000 come back out. Under harsh enough light, at the right angle, with the right instrument, you can still find the edge. Every black we have ever manufactured is a very good approximation. A black hole does not approximate, it returns nothing, not almost nothing, not a vanishingly small fraction. Nothing. Which makes it the only object in existence that satisfies the definition we have been using this whole time. Everywhere else, darkness has turned out to be a shortage of light, or a shortage of the right detector, or an accident of where we happen to be standing. Only there does the darkness belong to the object itself. We have measured comets and craters, asteroids and event horizons. We have quantified how little light comes back from each one, down to fractions of a percent. But every one of those measurements was made by the same instrument, not the telescope, the thing behind it. Because the entire time we have been asking how dark space is, we have been assuming the observer is a fixed point, a neutral witness, a camera that simply records what arrives. The human nervous system is nothing of the kind, and what happens to it when the light genuinely stops arriving, when the input drops not to a trickle but to zero, is stranger and more disturbing than anything we have found out there. Start with how much of you is dedicated to seeing. A figure gets quoted often, that roughly 30% of the human cortex is involved in vision. Treat that number carefully because it is genuinely contested. The answer depends entirely on how you count. Many brain regions handle more than one sense at once, and drawing a hard border around visual territory is a judgment call, not a measurement. But nobody disputes the underlying point. Vision is our dominant channel by a wide margin. Consider how you actually move through a day. You cross a road by watching for gaps. You find one person in a crowded station by scanning faces. You decide whether a stranger approaching you is friendly or angry in a fraction of a second from the geometry of their eyebrows and mouth. Navigation, threat detection, social reading. 3 of the most important things a human being does, and all 3 run primarily on light. Now take the light away completely, and something has to happen to all that machinery. Before that, understand how little it takes to keep the system running. In 1942, 3 researchers, Selig Hecht, Simon Schleyer and Maurice Pirenne, designed one of the most elegant experiments in the history of perception. They sat their subjects in complete darkness for 40 minutes until the rods reached full sensitivity. They used light at 510 nanometers, precisely the wavelength rods respond to best. They fired flashes lasting 1,000th of a second, and they aimed those flashes 20 degrees off-center at the exact patch of retina where rod cells are packed most densely. Under those conditions, they found that between 5 and 14 absorbed photons were enough to produce a conscious visual experience. And here is what makes that number remarkable. Those 5 to 14 photons landed across a retinal area containing roughly 500 rod cells, which means almost every rod that fired had caught exactly 1 photon. 1. Your eye is not merely sensitive. Your eye operates at the physical floor of what light can be divided into. Whether that floor sits at 5 photons or 1 remains a live argument. Modern quantum light sources reopen the question, and the statisticians and the experimentalists have not reconciled. But out past the last street lamp, past the atmosphere, out where we have been travelling, the debate stops mattering entirely, because the number arriving is not 5, not 1, 0, and a detector capable of responding to a single photon behaves exactly like a broken one when nothing arrives at all. So what does a brain do with a channel that has gone permanently silent? It does not wait politely. It repurposes. In 2008, a team including Lotfi Merabet and Alvaro Pascual Leon blindfolded normally sighted adults, completely, continuously, for 5 days, while putting them through intensive tactile training. Not weeks, not months, 5 days. By the end, brain scans showed the occipital cortex, the visual cortex, the region that had processed sight since infancy, lighting up in response to touch, and this was not incidental. When the researchers temporarily disrupted that region with magnetic stimulation on the 5th day, the blindfolded subject's ability to read Braille characters got worse. The control group, unblindfolded, showed no such effect. Then the blindfolds came off. Within 24 hours, the change had vanished. Think of a warehouse whose supplier stops delivering. Within days, the neighbouring departments move their own stock into the empty floor space. The moment the supplier returns, they are evicted just as quickly. Your brain does not hold territory open out of loyalty. 5 days of darkness and the eviction notice is already served. But repurposing is not the strangest part. The same research group had documented something earlier. Sighted people, blindfolded long enough, begin to hallucinate. The pattern shows up everywhere the input stops. In Ganzfeld experiments, where subjects stare into a completely uniform, featureless visual field, often created with halved ping-pong balls over the eyes under even light, healthy people start seeing structure that is not present. Shapes, movement, eventually scenes. Miners trapped underground have described it. Cavers in unlit chambers. Long-haul solo sailors on night watches, and drivers on empty roads after too many hours. The phenomenon has an old, unofficial name, the prisoner's cinema. Formless light at first, then geometry, then sometimes figures. Flotation tank research follows a similar arc. Deep relaxation in the early phase, then imagery the person did not summon. And medicine has a formal version. Charles Bonnet syndrome occurs in people losing their sight, often from macular degeneration. As visual input fades, the brain begins generating vivid, detailed hallucinations, faces, patterns, entire landscapes. The patients typically know perfectly well the images are not real. That knowledge does not stop them, which points at something fundamental about what you are. Your visual system is not a camera. A camera records what arrives and nothing else. Your visual system is a prediction engine, constantly generating a model of the world and checking it against incoming data, correcting as it goes. The image you experience is largely constructed, then edited by reality. Remove reality, and only the construction remains. Like a microphone in a silent room, turning up its own gain until it starts hearing itself. So here is the honest answer to what you would see in true darkness. Not nothing. You would see something, and none of it would be out there, which makes the next part genuinely unsettling, because in space, something does. In July of 1969, during the debriefing after Apollo 11, Buzz Aldrin reported that he had been seeing flashes of light in the cabin after his eyes had dark adapted with his eyes open or closed. Pinpoints, thin streaks, small clouds of light moving across his visual field, almost always colorless. Once the report started, NASA briefed later crews to watch for them, and the observations became deliberate. Astronauts counted rates that varied by report and by orbit, from roughly one every few minutes up to a couple per minute, often enough to be a real problem for anyone trying to sleep. And remarkably, someone had called it in advance. In 1952, 17 years before Apollo 11, the biophysicist Cornelius Tobias predicted that people exposed to cosmic radiation beyond Earth's shielding might perceive exactly this kind of thing. Turning a crew anecdote into science meant catching the cause and the sensation in the same instant. On Apollo 16 and 17, astronauts wore a device strapped to the head, the Apollo Light Flash Moving Emulsion Detector, which recorded the tracks of charged particles while the wearer pressed a marker each time he saw a flash. The work continued on the Russian station Mir with an experiment called SIL-I, short for Silicon Eye. Roughly 50 observation sessions between 1996 and 2000, 10 astronauts, more than 200 flashes logged against silicon particle detectors. Then Altair carried it onto the International Space Station. The records lined up. Heavy, high-energy atomic nuclei and energetic protons, cosmic rays, flung across the galaxy by violent events, were what set the flashes off. But how they set them off remains unsettled on two separate fronts. The first question is where. The leading view holds that the particle ionizes tissue directly in the retina, punching through the light-sensing cells and exciting them as though they had caught a photon. Ground experiments with heavy ions support this, but some flashes may come from particles striking the optic nerve or deeper in the visual pathway entirely, producing a sensation of light with the retina uninvolved. The second question is what? Alongside direct ionization, there is Cherenkov radiation. When a charged particle crosses the clear jelly inside your eye faster than light, travels through that fluid, it emits a genuine faint glow, real photons manufactured inside your own eyeball. That mechanism is well established in physics and has been demonstrated in patients undergoing radiation therapy. The trouble is the description. Cherenkov light should appear bluish and diffuse. Most astronauts reported sharp white points and streaks. The two do not match well. Both processes probably contribute. Which one dominates has not been settled. Now place yourself there. You are strapped into a couch on the way to the moon, lights down, eyes closed, drifting towards sleep. A thin white streak crosses your vision from left to right. Nothing entered your eye. Nothing was there to see. A nucleus, accelerated by something enormous and violent, possibly a supernova on the other side of the galaxy, has just passed through your skull. And this is the part that stays with me. Those flashes are the only component of the space radiation environment a human being can perceive at all. You cannot feel radiation. You cannot smell it or hear it. The dose accumulates silently, every second, doing whatever it does to your cells. The only sensory contact you will ever have with it is an occasional spark behind closed eyelids. Meanwhile, Something separate is happening to the hardware, and this one has nothing to do with darkness. On Earth, gravity pulls the fluids in your body downward all day. Remove gravity, and that fluid shifts toward the head and stays there. The consequences show up in the eyes. Astronauts on long-duration station missions develop what NASA calls spaceflight-associated neuroocular syndrome, optic disc edema, swelling where the optic nerve enters the retina, appears in roughly 70% of them on extended flights. The back of the eyeball flattens slightly. The refractive shift degrades near vision, sometimes by enough to require new glasses in orbit. The mechanism is still not fully understood, and some of the changes persist after landing. NASA now classifies it as a critical risk for Mars-class missions. The sense we depend on most is the one space attacks first. Underneath all of this sits something much older. For nearly the whole of human history, darkness meant three specific dangers: predators you could not see, terrain you could not judge, so you fell, and injuries you could not avoid because you never saw them coming. Night was not atmospheric for our ancestors. Night was lethal. That is why fear of the dark is close to universal in children, and why it never fully leaves. Most adults will admit to a flicker of unease walking down into an unlit basement. Not one of them believes anything is actually down there. The reaction is not rational, and it does not care. Now take that machinery into space and watch it fail in the opposite direction. Nothing is hiding out there. Nothing could be. The vacuum contains no predator, no ambush, no edge to stumble over. Every fear our species evolved about darkness concerns what darkness conceals, and this darkness conceals nothing at all. That is exactly what makes it worse. The dread is not that something is there. The dread is that nothing is. So we tried to study it on the ground. On June 3rd, 2010, 6 men, 3 Russians, 2 Europeans and 1 Chinese participant, were sealed into a facility at the Institute of Biomedical Problems in Moscow. 550 cubic meters, about 19,000 cubic feet, roughly the volume of a modest family house. They stayed inside for 520 days, with artificial communication delays of up to 20 minutes each way. 520 days is longer than a full pregnancy with half a year added on, and they never once stepped outside. The project was called Mars 500, and it ran to completion. No interpersonal conflicts serious enough to stop the experiment. No crisis. But the data underneath told a different story. Matthias Basner at the University of Pennsylvania analyzed the crew's sleep and found it steadily degrading. The men slept more as the mission went on, while drifting out of alignment with the imposed day-night schedule. Their bodies quietly lost their grip on time, and researchers identified something they named the detachment effect. As communication delays stretched, the crew simply talked to mission control less. On the surface, that looks like healthy autonomy, which any real Mars crew will need. Dmitry Shved of the Russian Academy of Sciences pointed at the other edge of it. When the crew stops communicating, mission control loses the ability to understand what the crew needs, and therefore loses the ability to help them. The same detachment pattern turned up again in the later Sirius isolation studies. NASA's HIC's analogues in Hawaii added their own variations from 2013 onward, and most recently, Shapea. The first mission sealed 4 volunteers into a 3D printed habitat on June 25, 2023, and released them on July 6, 2024, 378 days, with communication delays up to 22 minutes, simulated Mars walks, and vegetables they grew themselves, which is why behavioral health has stopped being treated as a soft consideration. Space agencies now budget for it the way they budget for oxygen and shielding, a mission-critical system with failure modes, countermeasures and monitoring. But every one of these studies shares the same limitation, and the researchers are the first to say so. The Mars 500 crew knew Moscow was on the other side of a door. The Shapea crew knew Houston was a few hundred meters away, and that a medical emergency meant somebody opening a hatch. Every analog has a wall, and behind every wall is a planet full of people. No experiment has ever placed a human being somewhere they could look out a window at genuine, unbounded nothing. For months, with the Earth reduced to a point of light and no possibility of turning back. We do not know what that does. We are extrapolating from confinement studies and blindfold experiments and the reports of solo sailors, and hoping the extrapolation holds. But a very small number of people have come closer to it than anyone else alive. A handful of them looked directly into it, with no Earth in the window, no radio contact, and nothing at all to give them a sense of where they were. What they said afterward is the closest thing to data we have. 3 men went first. In December of 1968, Frank Borman, Jim Lovell, and Bill Anders rode Apollo 8 out of Earth orbit, the first human beings ever to leave. Every person who had flown before them had stayed inside a few hundred kilometers of the surface, circling a planet that filled the window. Apollo 8 went to the moon, and once there, the spacecraft did something no crew had experienced. On each orbit, it passed behind the lunar far side, and the moon, a solid ball of rock about 3,400 kilometers across, roughly 2,100 miles, sat directly between the astronauts and Earth. Radio waves do not bend around a mountain, let alone a world. Contact simply stopped. For roughly 45 minutes at a time, those 3 men were the most isolated human beings who had ever lived. No Earth in any window, no voice from Houston, nobody on the planet with the faintest idea whether they were alive. And when they looked out, they found nothing to look at. Lovell described a darkness that did not read as empty. It read as infinite, a distinction that sounds like poetry until you understand the physics behind it. The stars were there, but stars are useless for judging distance by eye. A point of light gives you no parallax, no apparent size, no texture. Your brain cannot tell whether it sits a kilometer away or 40 trillion. Like being handed a photograph of a ceiling covered in pinpricks and asked how large the room is. The information is not dim. The information does not exist. On December 24th, 1968, Anders picked up a camera and made what many people consider the most consequential photograph of the 20th century. Earthrise, our planet lifting above the lunar horizon, blue and white and small. But notice what actually gives that image its force, because almost nobody says it out loud. Earth is not blindingly bright in that frame. What makes it overwhelming is that everything else is absolutely black. Our world is the only object in the picture with colour, with edges, with weather. It hangs there as the single exception in a field of pure nothing. Take away the blackness, and the photograph is a snapshot of a planet. Apollo 17 made the same point again in December of 1972, with the image we now call the blue marble. Earth fully lit, whole, unaccompanied. No context, no neighbours, nothing nearby to compare it to. The dark did not spoil those photographs. The dark composed them. And then, in April of 1970, the dark stopped being scenery. 2 days into Apollo 13, an oxygen tank ruptured. The command module lost power, water and breathable air, and the crew, Lovell again, with Fred Hayes and Jack Swigert, moved into the lunar module and used it as a lifeboat. A vehicle designed to keep 2 men alive for about 2 days now had to keep 3 alive for 4, which meant shutting almost everything down. Guidance systems, heaters, most of the lighting. The cabin temperature fell to around 3 degrees Celsius, about 38 Fahrenheit, roughly the inside of a domestic fridge. Condensation formed on the walls and instrument panels. The crew could not sleep properly. They rationed water down to a few ounces a day, and they spent those days in a cold, dark, cramped machine, further from Earth than any humans had ever been, with survival genuinely uncertain. Lovell reflected later on what disturbed him most about the void out there. Not that it was hostile. Hostility would have implied attention, something aware of them, working against them. The dark was simply indifferent. It would not have registered their deaths in any way at all. That is a colder thought than fear. A room that does not know you walked into it. Then, for more than half a century, No human being went back. That changed on April 1st, 2026. At 6:35 in the evening Eastern Time from Launch Complex 39B in Florida, the Artemis II crew lifted off. NASA astronauts Reed Wiseman, Victor Glover and Christina Koch with Canadian Space Agency astronaut Jeremy Hansen. They did not land. They looped around the far side of the moon and came home after a mission of nearly 10 days, splashing down in the Pacific off San Diego on April 10th. At their furthest point, they were 252,756 miles from Earth, the greatest distance human beings have ever traveled, breaking a record that had stood since Apollo 13 set it accidentally while fighting to survive. The path forward from there has been redrawn. In February of 2026, NASA restructured the program. Artemis III, originally the return to the surface, became a low Earth orbit mission to test docking with the commercial landers being built by SpaceX and Blue Origin. The first crewed landing moved to Artemis IV, targeted for 2028. The reasoning given was blunt. Jumping straight from a lunar flyby to a lunar landing was judged too large a step, which is a fair description of the whole problem. Going out there remains extraordinarily difficult, and we have not gotten meaningfully better at it in 50 years. Our machines had no such limitation. In 1977, NASA launched Voyager 2 in August, and Voyager 1 in September, aimed at a planetary alignment that occurs roughly once every 176 years. What they returned in the following 12 years rewrote the outer solar system. Io, a moon of Jupiter, turned out to be violently volcanic, the first active volcanism ever found beyond Earth, discovered in a navigation image. Europa showed a cracked shell of ice, the first hint of an ocean beneath. Titan hid behind a thick orange haze. Triton, at Neptune, was found firing nitrogen geysers into space at a temperature near -235 Celsius. Saturn's rings, which look from Earth like a handful of smooth bands, dissolved under Voyager's cameras into thousands of individual ringlets, braided, kinked, structured on scales nobody had predicted. And Neptune, receiving barely any sunlight at all, turned out to have the fastest winds in the solar system, moving faster than the speed of sound at sea level on Earth. Then, on February 14, 1990, Voyager 1 turned its camera around from about 6 billion kilometers out, roughly 3.75 billion miles, and photographed home. Earth came out as a fleck less than a single pixel wide, caught in a band of scattered sunlight, the pale blue dot. Voyager 1 crossed into interstellar space in 2012, and today it sits roughly 15.8 billion miles from Earth, travelling at about 61,000 kilometers per hour, 38,000 miles per hour, toward the constellation Ophiuchus. On November 18, 2026, it crosses a line nothing built by human hands has ever crossed. At 16.1 billion miles, 25.9 billion kilometers, it becomes the first object a full light day from Earth. Understand what that means operationally. Send Voyager a command on Monday morning, and it arrives Tuesday morning. If it answers, you hear the answer Wednesday. Every question and reply costs 2 days, and the spacecraft asking to be kept alive is running out. Its power comes from 3 radioisotope thermoelectric generators, fueled by decaying plutonium. At launch, they produced about 470 watts. Today, they produce roughly 250, about what a couple of old-fashioned incandescent bulbs would draw, and that figure falls by around 4 watts every year. Voyager 1 launched carrying 11 scientific instruments. As of April 2026, 2 are still switched on: the magnetometer and the plasma wave subsystem. The cosmic ray subsystem went dark in February of 2025. The low-energy charge particle instrument followed in April of 2026. Engineers have shut off heaters, moved to backup thrusters, and arrayed multiple antennas just to hear a transmitter putting out around 23 watts from beyond the heliosphere. By roughly 2036, the signal will be too faint for any antenna on Earth to detect. And this is the part that stays with you. Voyager will not stop on that day. Voyager will keep flying, keep pointing, quite possibly keep transmitting into a universe that no longer has anyone listening. It will simply cease to be heard. Bolted to its side is the golden record. Sounds of Earth, images, greetings in dozens of languages, pressed into gold-plated copper. In about 40,000 years, it passes within a couple of light years of a faint star called Gliese 445. 40,000 years ago on Earth, the last Neanderthals were still alive, and human beings were painting animals on cave walls by firelight. That is how far ahead the record's first appointment sits. One more machine matters here, for a reason that has nothing to do with distance records. New Horizons reached Pluto on July 14, 2015, and then, on January 1, 2019, flew past a small Kuiper Belt object called Arakoth, the most distant object ever explored up close. Now, Pluto is instructive about what dark actually means, because the intuition is wrong. At noon on Pluto's surface, sunlight arrives at roughly 1/900th the strength it has on Earth. That sounds like blackness. It is not. NASA calculated the equivalent as the light outdoors at dusk, bright enough that you could comfortably read a book. But raise your eyes from the page. Pluto's atmosphere is so thin it scatters almost nothing, which means the sky above you at midday is not blue, not grey, not dim. It is black, full of stars, at noon, while your hands are lit well enough to work by. And that thin, dust-free environment is exactly why New Horizons has become something nobody planned. Out beyond the haze of interplanetary dust that ruins every measurement made near Earth, the spacecraft now doubles as the darkest sky observatory our species operates, which points at something quietly profound about all of this. Distance itself became a scientific instrument. Some measurements are not merely harder from home, they are impossible from home, at any budget, with any technology. To take them, something has to physically leave. So we have sent eyes outward, and across every wavelength from every vantage point, one particular expectation has failed to materialize. No city lights on the night side of any world we have examined. No structures wrapped around any star. No engineering signature in any spectrum. No unambiguous signal in more than 60 years of listening. The Fermi paradox usually gets framed as a question about aliens. Framed accurately, it is a question about darkness. Our galaxy is roughly 13 billion years old. Our Sun formed about 4.5 billion years ago, which makes it a relative newcomer. Billions of stars in the Milky Way are considerably older, and any civilization arising around them would have had a head start measured in geological time. Even at modest speeds, a determined expansion would cross the galaxy in a few tens of millions of years, a rounding error against 13 billion. The galaxy should be visibly occupied. It is not, and 3 families of explanation remain standing, none of them falsified. The first is rare Earth. The conditions that produce complex life may be far more improbable than we assume. The right star, the right orbit, plate tectonics, a large stabilizing moon, a gas giant clearing the neighborhood, and billions of uninterrupted years. Under this reading, the silence is honest. Almost nobody is out there. The second is the Great Filter. Something reliably prevents civilizations from persisting and spreading, and the filter has 2 versions. Either it sits behind us, some transition already passed, meaning we were extraordinarily lucky, or it sits ahead of us, waiting, and every civilization reaches it eventually. The third is the least dramatic, and possibly the most likely. We have barely looked. Our surveys have covered a small fraction of the sky, across a narrow slice of frequencies, for a short window of time, listening for signals resembling the ones we happen to make. Concluding the galaxy is empty on that basis is like scooping a glass of water from the Pacific, finding no fish, and declaring the ocean sterile. We cannot currently distinguish between these, not because scientists are being cautious for form's sake, but because the evidence genuinely does not separate them. Everyone who has gone out into the dark has come back with the same report. Borman, Lovell and Anders behind the Moon, Voyager beyond the heliosphere, New Horizons past Pluto, every antenna pointed at every promising star for 6 decades. The dark has answered nothing, so far. And yet the darkness we keep looking into is not a permanent fixture of reality. Run the universe backwards far enough, and you reach a moment when no dark existed anywhere, no shadow, no night, no gap between anything, because every direction blazed. Run it forward far enough, and you reach the opposite, a state where the darkness becomes total and final, and stays that way essentially forever. We are living in the brief interval between those two conditions, and that interval, the era when stars burn, when light is available, when observers can exist to notice any of it, turns out to be a vanishingly thin sliver of cosmic history. The universe had a first darkness. It will have a last one. And there is a third darkness in this story, much smaller, much closer, and the only one we are personally responsible for destroying. Go back far enough, and the universe had nowhere for a shadow to fall. In the first few 100,000 years after the Big Bang, everything that existed was packed into a hot, dense plasma, atomic nuclei and free electrons, moving too fast and too energetically to bind together into atoms. And free electrons are extremely good at one particular thing, knocking photons sideways. Light could not travel. A photon would move a tiny distance, strike an electron, scatter, strike another, scatter again, a random stagger in every direction going nowhere. You have stood inside something like this. Dense fog, lit from all sides at midday. Photons are pouring at you from every angle. The whole world is blindingly bright, and you cannot see your own hand at arm's length. Not because light is missing, because light cannot travel in a straight line. The early universe was that, everywhere, at once, opaque, glowing, and completely without darkness. Then expansion cooled it, and at roughly 380,000 years after the beginning, electrons finally slowed enough to bind to nuclei and form neutral atoms. Cosmologists call it recombination. The free electrons vanished into atoms, and the fog lifted in an instant. 380,000 years sounds long, but scale it against the universe's full 13.8 billion. If you compressed all of cosmic history into a single 80-year human life, recombination would happen less than a day after birth, and the light released at that moment, freed all at once to travel in straight lines for the first time, is still traveling. Stretched now into microwaves, it fills every direction we look. The cosmic microwave background is the oldest light that exists, and it is a snapshot of the day the universe stopped being opaque, which is also the day darkness was invented. What followed has a formal name: the Cosmic Dark Ages. No stars, no galaxies, nothing burning anywhere in the universe. Just neutral hydrogen and helium drifting through expanding space, while the afterglow of recombination redshifted steadily out of visibility. Millions upon millions of years of a cosmos that contained matter, contained physics, and contained no light source at all. We have almost no direct information about that era, because darkness leaves nothing to photograph. Almost. Neutral hydrogen has one faint signature. Occasionally, the electron in a hydrogen atom flips the orientation of its spin, and the atom emits a radio wave about 21 centimeters long, roughly 8 inches, the length of a large kitchen knife. Cosmic expansion stretches that signal, so light emitted during the Dark Ages arrives today at much longer wavelengths. Find that stretched signal, and you have a direct measurement of an era with no stars in it. In 2018, a team led by Judd Bowman announced exactly that. Their experiment, EDGES, reported an absorption feature near 78 megahertz, corresponding to hydrogen at a redshift around 17, roughly 180 million years after the beginning. Except the signal was strange, unusually deep, and oddly flat-bottomed. Explaining it would require either an unknown source of radio background or some non-standard mechanism cooling the gas. In other words, new physics. Then, in 2022, the SARAS-3 experiment looked for the same feature and did not find it. The team reported a non-detection, rejecting the edge's profile at 95% confidence and concluding the earlier signal was most likely contamination from the instrument itself or the sky in front of it. The disagreement has not been settled. Two careful teams, one claiming the first glimpse of the cosmic dark ages, the other saying the glimpse was an artifact, and that impasse is now driving one of the more remarkable proposals in astronomy, putting radio telescopes on the far side of the moon, the only place in the accessible universe permanently shielded from Earth's radio noise. The Dark Ages ended when the first stars ignited, somewhere around 100 to 200 million years after the beginning. Astronomers call them population 3 stars, and they were made of almost nothing but hydrogen and helium, because in that universe nothing else existed. No carbon, no oxygen, no iron. Those first stars built them, fused them in their cores, and blew them outward when they died, which makes this personal. The carbon in every cell of your body, the oxygen filling your lungs right now, the iron in your blood carrying that oxygen, every atom of it was manufactured inside stars that had to burn and die before any of it could exist. You are, quite literally, assembled out of the first things that ever ended the dark, and the picture is currently under revision. JWST keeps finding early galaxies brighter and more assembled than the models predicted. Not a crisis, but a real tension. Either galaxies came together faster than we thought, or our understanding of early star formation needs work. Now here is a fact that reframes the present. Star formation across the universe peaked roughly 10 billion years ago, in an era astronomers call cosmic noon. Gas was abundant, galaxies were colliding constantly, and stars were being born at rates the universe has never matched since. That peak is behind us. Gas gets consumed and locked into stellar remnants faster than it gets recycled. The rate of star formation today is a small fraction of what it was. We are already living after the brightest era the universe will ever have, not approaching the peak, descending from it. We arrived in the late afternoon. Look forward, and the picture divides in two. Our local group, the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, is gravitationally bound. Gravity holds it together against expansion, and it will stay together. Everything outside it is receding, and will eventually recede beyond visibility. What happens inside the local group has just become unexpectedly uncertain. For decades, a Milky Way-Andromeda merger was treated as near certain. Then, in 2025, Till Sawala and colleagues at the University of Helsinki published new simulations in Nature Astronomy, using updated Hubble and Gaia measurements and, crucially, including the gravitational effects of the Large Magellanic Cloud and Triangulum. Their result? Roughly a 50-50 chance of a merger within the next 10 billion years. A head-on collision came in at under 2%. Sawala summarized the shift precisely. The probability went from near certainty to a coin flip. Whatever happens locally, the long ending is not in question. The stelliferous era, the age of stars, continues until the gas runs out. Based on current estimates, that takes roughly 100 trillion years, sustained at the end by red dwarfs so miserly with fuel that they burn for trillions of years each. 100 trillion is more than 7,000 times the entire current age of the universe. Everything that has ever happened, recombination, the first stars, cosmic noon, the formation of Earth, all of biology, all of human history, occupies less than 1/100th of 1% of that span. Then the degenerate era. White dwarfs cooling slowly into black dwarfs, neutron stars, occasional collisions producing the last supernovae in a mostly dark cosmos. Fred Adams and Greg Laughlin calculated that a white dwarf fueled by proton decay would radiate around 400 watts, a few household bulbs. An entire galaxy of them would shine more dimly than our single sun does today. But that stage rests on something nobody has ever seen: proton decay has never been observed. Experiments like Super Kamiokande have watched enormous tanks of water for decades without recording a single confirmed event, pushing the proton's minimum lifetime to staggering values. If protons are genuinely stable, the entire schedule changes. Then the black hole era. Every remaining structure has evaporated or been swallowed, and only black holes remain, themselves leaking Hawking radiation, shrinking imperceptibly over spans from around 10 to the 67th years for a stellar mass hole to 10 to the 100th for the largest. That last number deserves a moment. The observable universe contains roughly 10 to the 80th atoms. 10 to the 100th years is a number that exceeds the total atom count of everything by a factor of 100 billion billion. And after that, the dark era. Maximum entropy, heat death. Understand what that means, because the phrase misleads. Nothing burns out. Instead, every temperature difference in existence evens out. And a difference is what makes anything happen at all. An engine needs hot against cold. A star needs a dense core against cool space. A cell needs a chemical gradient. Remove every difference and the universe does not end. It simply becomes unable to do anything forever. Not a fire going out. A fire that has spread so perfectly evenly that nothing anywhere is warmer than anything else. Though even this may need rewriting. If the hints of evolving dark energy hold up, the far future changes. How fast expansion proceeds, how cold things get, what the final state actually looks like. The ending is written in pencil, which brings us back to the only darkness we can personally affect. The 2016 World Atlas of Artificial Night Sky Brightness, led by Fabio Falci, found that more than 80% of the world's population lives under light-polluted skies, and more than 99% of people in the United States and Europe. The Milky Way, the thing that gave our galaxy its name, visible to every human generation before roughly the last three, is now hidden from more than a third of humanity. Nearly 80% of North Americans have never seen it from home, and it is accelerating. In 2023, Christopher Kyber and colleagues published an analysis in Science of 11 years of citizen science observations through the Globe at Night project. Ordinary people worldwide comparing their sky against a set of star charts. Between 2011 and 2022, the data implied sky brightness rising by about 9.6% per year globally, 6.5% in Europe, 10.4% in North America. Kyber translated that into the only unit that matters. A child born somewhere with 250 visible stars would see roughly 100 by their 18th birthday, and satellite instruments disagree. They suggest closer to 2% per year. The gap turns out to be an instrument problem, not a contradiction. The satellite sensors measure wavelengths from about 500 to 900 nanometers, which largely misses the short wavelength blue light of modern white LEDs now dominating city lighting. Human eyes are seeing something our satellites are built not to notice. The most recent development comes from orbit. More than 14,000 satellites currently circle Earth, the majority belonging to a single telecommunications constellation. Current filings and proposals would add more than 1.7 million. In July of 2026, the European Southern Observatory published the first study calculating not just satellite streaks across images, but the effect of constellations on the brightness of the whole sky. Olivier Hainaut's analysis found that faint satellites contribute a diffuse veil, while bright ones scatter light through the atmosphere in every direction. His numbers: 5,000 large reflective satellites would raise sky brightness worldwide by up to 30%. 50,000 would raise it by as much as 300%. The entire night sky, everywhere on Earth, 3 times brighter than it is now. Under that scenario, images from the Vera C. Rubin Observatory, currently beginning a 10-year survey of the southern sky, would be largely unusable. And from anywhere on the planet, Hainaut noted, the sky would resemble what you see from a city's outer suburbs. The recommendation is a cap, No more than 100,000 satellites, all faint enough to sit below naked eye visibility. Mitigation efforts so far have produced mixed results. Darkening treatments and sunshades have helped some designs and not others. Meanwhile, the effects reach past astronomy. Artificial light at night suppresses melatonin and disrupts circadian rhythms in humans. Migratory birds navigating by stars become disoriented over lit cities. Insects, hatchling sea turtles, nocturnal predators, and the plants that time their year by day length are all responding to a signal that no longer means what it meant for the whole of their evolutionary history. Against that, a small counter-movement. Dark sky preserves, protected by ordnance. Bortle Class 1 sites, the darkest rating on a 9-point scale, where the Milky Way is bright enough to cast a faint shadow on the ground. People are now deliberately protecting darkness. That sentence would have been incomprehensible to every human being who lived before about 1900. So come back to where this started. The same room, the same bed, curtains still drawn, light still bleeding under the door, the same faint charger glow you never notice. Nothing in that room has changed. What has changed is what it means. Space is dark for 3 reasons, and they are all simple. Because almost nothing is in it, so light passes through without ever revealing itself, because the universe is young enough that most of its light has not arrived, and because space expands, stretching what does arrive out of the narrow band your eyes were built to catch. Those are not gaps in our knowledge, those are the answers. And the strange thing, the thing worth carrying out of this, is how the relationship inverts once you see it properly. The dark is not an interruption of the normal state of things. The dark is the normal state. Light is the rare condition, local, temporary, generated by a small number of burning objects scattered impossibly far apart in the brief geological instant of cosmic history when burning is still possible at all. The pocket of light we live inside is not one bubble. It is bubbles nested inside bubbles, a lit room inside a lit planet, inside the reach of one ordinary star, inside a galaxy that is one lamp among billions, inside a thin sliver of time between a universe that could not hold shadows and a universe that will hold nothing else. We keep describing ourselves as looking out into the darkness, as though we were standing somewhere solid and peering into something foreign. That was never the picture. We are the small light inside it, briefly, improbably, and for now, still bright enough to see each other by. Think about that photograph one more time. Earthrise, the most reproduced image of the last century, and nothing in it is bright. Our planet is a dim thing lit by a distant star, no more luminous in absolute terms than a piece of wet stone. It overwhelms you because it is the only thing there. The blackness did not spoil that picture. The blackness composed it. Take the void away, and you have a snapshot of a planet. Leave the void in, and you have the reason anyone ever looked twice. That is worth carrying with you tonight, because the same arithmetic applies much closer to home. You are not small against all that nothing. You are visible because of it. Everything you love is rare in exact proportion to how much emptiness surrounds it. The people in the next room, the ordinary Tuesday you will forget, the fact that matter arranged itself carefully enough just once to sit somewhere quiet and wonder about the dark. The dark was never what made you small. It is the only reason anything about you shows up at all. Thank you for staying with me through all of it. If this journey meant something, a like and a subscribe are how you tell me, and there are quieter, stranger ones still to come. I hope you'll be here for them. Sleep well tonight. You are the lit thing in the frame.